provide software for the oil and gas industry. So what we do is we provide data analytics and aggregation. We will work a lot with geospatial data and displaying geospatial data to our clients. And so my job there is to work with PostGIS and PostGIS in particular to run analytics on our data. So this talk is going to go over PostGIS and several of its major features. So what PostGIS is it's a plugin for PostGIS that allows you to work with any kind of geospatial data. But for this talk, I'm going to limit it to just the geographic data in the 2D, although it can handle 3D stuff and other kinds of data as well. So to begin, let's take a look at a few different ways that a computer can store geometric data. And so there's two main ways, vector and raster. And so what vector is it's storing the data as a list of points that outline the geometry. So this works really well for if you have solid body polygon, solid color polygons, because it allows you to get very crisp edges and high resolution lines as well. The alternative is raster data. So raster works a lot better for data that's defined on a per pixel basis. It also can be used to speed up your polygon data. If you have a lot of polygons and want to display that to the user all at once, one of the options would be to use raster, as we'll see in a little bit how that helps. Its disadvantage is it doesn't have the crisp boundaries, so when you zoom in, raster data becomes pixelated a lot. So to begin, let's take a look at some of the ways we can use vectors in our data set. So there's three different types of vector data that we work with a lot, and the first type is point data. So this is an example point data set which shows the populated places in the United States. A lot of times you'll store your point data with a lot of metadata as shown here, and you just depending on what your mapping software does, you can show it in a bubble or other ways. So to get your point data into PostGIS, you have two main options. You can copy it from a CSV using the standard copy from syntax. And once you bring in your data from a CSV, you'll usually have three columns, or at least a longitude column and a latitude column, and sometimes a spatial reference identification column. So you can convert those columns into a PostGIS type using stMakePoint. stMakePoint will take those long and lats and put it in a form that PostGIS can work with and optimize for. Then you can set your spatial reference identification using this. So what a spatial reference identification does is there's many ways that you can represent the three-dimensional sphere of Earth as a 2D map. And depending on where you're working or what data sets you're using, their choice of SRID varies. So it's pretty important that when you bring in your data, you make note of what SRID the data is in so that you can keep your data consistent. The other alternative is to use shape to pSQL. So what this function does is if you're bringing in a shapefile, which is pretty common for sending Polygon data across different softwares, you can use this function here to convert it to a SQL file and then load it in using pSQL as you would any other file. Another thing to notice is that you can also specify the transformation for your SRID. So that's what the -S option is doing there. It's bringing in this data as a web Mercator. The next type of data we work with is a lot is line data. So here's an example of the street data for all of Colorado. Sorry?
Did you say that the S was feeding you the web Mercator?
Oh,
That's not web Mercator. That's
did I say? Yeah, sorry, geographic.
WGS 84.
Yeah, WGS 84. Sorry, I said the wrong thing. Sorry. Okay, so this is our streets data set. That shows the the traffic as the color, which isn't coming out real well. But you can load in your line data by passing in a list of longitudes and latitudes into a function called stgeom from text. So what this is going to do is it's going to it takes well-known text and converts it into the internal representation for a line. Again, we're passing in the SRID. Something to notice is that the first and the last points are, or the last point is a repetition of the first point. And the reason we're doing this is to enclose that rectangle. So if we hadn't done that, the rectangle would not be closed on that last set. The last type of data we work with is Polygon Data, as shown here. So if you bring in your data as a line, you can convert it to a polygon using stmake polygon from line. So that's just how you bring in your data. So now that we have our data into the database, let's take a look at a few of the different ways we can work with that data. So this is an example of the addresses in Colorado. So suppose one day you're walking down a street in Denver and you're curious as to what the addresses nearby are. You can do that by specifying your current location and then doing a nearest neighbor search using this function here. And so what this function is doing is it's calculating the distance between your current location and the location to each of the points in the data set, and then using that distance as the order by parameter, and finally limiting it to the 7 closest locations to where you are. Another thing you could do is it's not just limited to finding the distance between 2 points. You can also do it between a point and line or other types of geometries. So that's what this is showing here, is if you're trying to find all the areas that are within 100 meters of a road, you could bring in your 2 data sets of streets and addresses, limit it to the street that you're interested in, and then use distance sphere to find the distance between the point and the line, and then limit it to things that are within 100 meters. There's a few other functions that are distance to spheroid, which are designed more for accuracy as opposed to speed. So which one you use depends on the application. Suppose that instead of just trying to find the area or the points that are within the distance to your road, you actually care more about the area that is a certain distance to your road. You could do that with stbuffer. So what this will do is it'll outline the area that's within the distance to the road, and I can adjust that parameter to adjust the size of that polygon. So on the left is the original data set, and on the right is that buffered Polygon data set.
Does that create a temporary table?
It outputs a geometry, so you can then save it using a create table. So that function at the bottom outputs a geometry of the outlined polygon. Another thing that might come up is if you're interested in searching, doing area searches, you can use the intersects function. So what I have here is I have 2 different data sets, my roads or my streets data and my county data. I'm selecting out Boulder County, and I want to find all the streets that are within Boulder County using geometric search. So I'm using intersects here, passing in both the geometries, and it'll return true for all the areas where these geometries intersect. And so that's limiting my search to just that area. Another thing that might come up is instead of just trying to find the polygons that overlap, I might be more interested in finding where they overlap. At what shape does that look like? So I have 2 area data sets as shown here. The first is districts and the second is counties. And I happen to know that in Longmont, the district boundary doesn't quite outline where the county is. So we can see that here by selecting out first my district, then my Boulder County, and then doing an ST intersection on those two, which will then return a new geometry which outlines the shared space between the two geometries. Something that I noticed when bringing in data, a lot of the times it's not exactly the way you want it. So if you're bringing in a data field that uses negative 180 to 180, but you're trying to store it as an unsigned value, or you want to keep all your stuff in the positive region, you could use ST shift longitude to fix your data. So that would take the negative 180 and throw it over to the positive region, and the values that are greater than 180 and throw them into the negative region. Something to notice that when you call this on a column, it'll do both. So if you're getting data that is very inconsistent, that has values that are both in the negative region and in the greater than 180 region, you'd have to add a check around this to make sure that your output was what you would expect. Another thing that might come up is when you bring in data, you'll have extra data, such as elevation. If you just want to work with two-dimensional data, you can get rid of that extra data using ST Force 2D. So another thing that comes up a lot is transforming between your projections. So as we had before, we get data in as a certain spatial reference identification, and we want to output it as a different spatial reference identification. We can do that using the ST transform function. The reason you might want to do this is if you have data from two different sources, it's likely that they're not going to come in as the same projection. And so to run your calculations, some of the calculations require that they be in the same reference. So the way we do that is we create our point and then send that point to ST transform and specify our target output, in this case WGS84, and our output value is along that, as we'd expect. So sometimes your data sets will be very high resolution, and that's really good if you want very accurate analytics. But when you go to display that to your user, it's a little bit hard. This line here shows a single river, which is almost 500 points. If you try to display several rivers to your user, that could be quite slow. So one way to get around this would be to use the ST simplify function, which you can pass in a tolerance, and it'll remove points to that tolerance, reducing the resolution while still following around roughly the same shape. So on the left there, I have the original, or the new, the simplified line, and then on the right, I have overlaid that so you can see what the error you might expect. And adjusting that tolerance either way will dictate how close of a representation you get. Now let's take a look at rasters. So a lot of your data will come in as either as a raster, but other times you'll be converting your vector data into raster. So the reason you might do this is for performance. Being able to display, send a raster back to your users allows you to make your performance more consistent as opposed to sending them back a huge amount of vector data. The disadvantage is, of course, when you zoom in, you get very pixelated raster data as shown here. So it's a trade-off between speed and precision. But there's a few ways around that, as we'll see in a second. So to fully understand rasters, let's take a look at how rasters are stored in the database. So if we wanted to make a raster of the entire Earth, that would be a very large image. So obviously, PostGIS doesn't store the entire Earth rasterized. It only stores the areas where you're interested, where you have interesting things going on. So in this example, I have a 4x4 rectangle that I want to place on the Earth. And the way I do that is by specifying the width and the height, but then also an upper left coordinate, which will say, tell PostGIS where this is on the Earth. And then you can also adjust the scale and other values, as we'll see in a little bit. why that's important. Something to notice here is that there's no data stored in those pixels yet. Each rectangle could store any number or any certain amount of information. So to tell PostGIS that we want to store stuff there, we can use st_add_band, which is going to say, this is what I want to store at each of these pixels. So in this example, I'm storing an 8-bit unsigned int at each of these locations. And I'm initializing that value to 7. So that means at each of these pixels, I can store a value between 0 and 255, which is what I want to do for this example. The last thing I might want to do is to manually enter in a few of the values at a certain location. So I can use st_set_values to do that. So what I'm doing is I'm specifying an offset and then a new data value for each of the values in that rectangle. Doing this by hand would be very tedious. And obviously, when you're bringing in data, you're not going to do this a whole lot. So PostGIS offers a lot of, or a function to bring in that data. So Raster To PGSQL allows you to bring in a huge number of data formats, ranging from GeoTIFF to PNG. The list is huge, but I've only listed a few. And it works pretty much the same way the previous function worked, as in it takes your image file and converts it into a SQL file. You can then load in that SQL file using pSQL, as we did before. Although sometimes when you're bringing in your data, you may have never seen it. So if it's a TIFF file, you probably opened it up to get a sense of what it looked like. But some of these other data types are kind of hard to know what it looks like if it doesn't open up in an image viewer. So one way to do that, to get a feel for what your data is to call st_quantile on your raster, and then that will return the limits on your data. So I'm looking at a digital elevation map right now, and I see a few things that are kind of interesting, in particular that my data is a decimal. And depending on what I'm doing, I might not want that decimal. So one thing I can do is I can convert that band from a double precision into an integer. So what I'm doing here is calling st_reclass and passing in a parameter of 16-bit unsigned int to convert that into a discrete value, which will allow me to work with, if I have other data that's in that format, it will allow me to make things consistent. Another thing to notice there is the 1 to 100 and 1 to 100. So what that bit of code is doing is it's the scale factor. So right now I'm not scaling at all. An input value of 44 is going to return an output value of 44. You can use that expression to normalize your data. As I'm showing here, so to multiply by 10, I might go from 1 to 100 to 1 to 10,000, and you see each of those values, it gets multiplied by 10. But it's not just limited to a single normalization. You can do a piecewise defined function and get your data out like that, which comes in very handy when you're trying to keep the values of your data consistent across multiple data sets. So now that we have our data in a format that we like and all normalized the way we want it, the next thing we want to do is to convert that data into an image file. So the way I found, or a common way to do this is to convert it to an PNG using st_as_png, which will output a binary, and then convert that into a hex representation and output that hex into a file. We can then use a Linux command to convert that hex into a PNG using xxd, as shown here. And so what that's going to do is that's going to output our image as an image file, which we can then throw onto the map using the location information that we had before. Something to notice is that our output image is grayscale, and the reason is we only had one band there. We could get a little bit more information out of, or make it a little bit easier to read if we add some color to it. So the way you might want to do that is to use the st_color_map function, which I'm using here to highlight the streets based off the traffic, annual traffic over. So what I'm doing here is on the left, you see a few numbers, 4, 2, 1, 0. So what that is that's the input value at that location in the band, and the output is shown in the color to the right of that value. Something to notice is that I haven't specified a value for the number 3. So what PostGIS is going to do is it's going to interpolate between the number 2 and 4, interpolate that color, and predict what color I want to put on the map there. So that's pretty handy if you're trying to do gradients over a elevation map like we did before. At this point, we've output our data, but it's just one giant image, which depending on your input data could be quite large, and you couldn't quite, displaying that to the user might be a little bit tricky. So there's a few things we could do to make this a little bit more manageable. So the first thing we could do is to convert our image to tiles. So converting to tiles, what that's going to do is allow us at high zoom levels to not display everything to the user. So when you're zoomed in, we only display the tiles that are within your view rectangles. So instead of displaying the entire Earth, we're displaying maybe 4 or 5 tiles total. There's 2 ways we could do that. We can either dynamically generate it for the viewport that the user has. Which would allow us to have like a only generate the data that the user is requesting. But I'm guessing that you have more than one user using this data, so you might want to cache that data and store it so that you can get an advantage from the preprocessor or preprocessing step. So that's what the alternative does, is standardizing that tile alignment. That's what a lot of client-side applications will expect, is something in the form of WMS or other stuff. So what we're doing is we're taking our original tile alignment, which is shown in blue here, and trying to put it on that red tile alignment, which even though it's going to add a few pixels on the boundaries, is a reasonable thing to do for the speed up benefits that we get from our client side and simplification as well on their end. So the way we're going to do this is we're going to first align up the tile to our new high resolution alignment, and then we're going to call ST tiles once again on it so that we can get the new tiles that are aligned properly. So to align it up, what I'm doing here is I'm going to first figure out where my target alignment is, and I'm using standard math to figure that out. The blue dot being where I am and the red dot being where I want to be. Something that I notice when I go to shift that image, though, is that I'm shifting it by a non-discrete number of pixels. And that's kind of a problem when dealing with rasters. You want to work a lot with discrete values because a lot of the operations are expecting that. So in order to convert this from 400.5 some pixel offset to a 400 exactly pixels, I can use ST snap to grid and pass in my new target alignment, and that will allow me to align that image. This is not actually shifting the image yet, though. It's just making it so that when I go about shifting it, I can actually do that. The next thing I'm going to do is I'm going to create a canvas, which is what I'm going to use to merge with my aligned original image to get my tiles. So the way I'm calculating this is I'm going to use my origin that I calculated a few slides ago and the scale of my original image so that I can keep everything consistent, and call ST union. So what ST union does is it takes several different images that you pass into it and converts it into one, or it merges them all into one image. And therethere's several different algorithms you can choose for it to use. The default is the nearest neighbor, I believe. So it's merging those two images together. And if I were to call ST retile on this at this point, I would get those black rectangles there and have the proper alignment for what my client side is expecting. At this point, We haven't actually adjusted the resolution of anything. We have just made it so that when you're zoomed in, you're not requesting all the tiles. That's not. That's half the process. The other part is to actually reduce the resolution so that when you zoom out, you're not requesting all those tiles anyway. So the way we're going to do that is we're going to use pyramid to reduce resolution. So what this is each of those rectangles is a 256 by 256 image. On the far left, we see that at that zoom level, we would be requesting far fewer images than at the far right. So we want to use the lower resolution when you're zoomed out, and as you zoom in, increase the resolution so that we don't get that pixelated view of the data. So the way we do that is using ST, one way to do it would be to use ST rescale. So what this function does is it adjusts the scale of my image. So if I pass in a single image, it's going to, and a depth, as shown in that table there, the pixel width or the number of pixels wide and number of pixels high, the images reduces as I go deeper. And so that's exactly what I want. When I'm zoomed out, I only want to request those 2 by 2 pixel image, but when I'm zoomed in, I want to request the high resolution. Something to notice about this, though, is it's kind of tedious. Well, if I wanted to take advantage of the pre-processing caches, I would want to store this into a table. And keeping track of those tables, which are kind of auxiliary tables in a way, could be kind of tedious. Luckily, PostGIS did provide a function to manage that. And that function is stCreateOverview. So instead of applying this to a single row, it's going to apply this to an entire column and create those tables for you. So you pass in a table, which is the first parameter, and a column, which is the second parameter, and it will generate the overview tables as shown here. So it makes things a lot easier for when you're working with different resolutions. Another thing that's pretty important to do is to make sure that your data is consistent. Because when you're working with tiles, having things that are perfectly aligned and exactly the right size is super important. So one way to do that is to add constraints to your table. So if you try to add a constraint to a table where it's invalid, it's going to throw an error. Or if you try to add invalid row to a table that already has a constraint, it's going to throw an error. And so that's a few of the constraints that I look for when I'm creating these tables is that my images all have the same width and height, scale, and spatial reference identification. But there's a few others that check for alignment, and they're a little bit too long to put in a PowerPoint. So now that we have our data into the database and we're displaying it to the user, we haven't done any analytics yet. We have just displayed what they requested back. So now let's take a look at a few of the things we can do to display that data back to the user in a meaningful way. So one of the functions that they have is ST hillshade. So if you pass in a digital elevation map and a direction of light, this will show you what hills would be illuminated based off that direction. So that's good if you're trying to find where are the northwest facing slopes in this area. And so that's what this map would represent. And you just pass in a raster there, that angle, and it'll output this raster here. Another thing it does is you can call ST slope to compute the slope at each of those locations on the digital elevation map, which might be helpful if you're doing analytics on steep slopes. Those are both implementations of a more generalized function called ST-map algebras. And so let's take a look at an example of what you can do with ST-map algebra. Suppose that I have a problem where I want to find the timberline across the map. And so what timberline is the area where trees stop growing because of elevation. But that's not always at the same place. There's kind of an epsilon or a error between that. So that's what that green band is the place where I think that tree line might be. And so what I would do is I could call this ST-map algebra function with a custom equation here. So what I'm setting up is just an equation that's saying at each pixel run this function. And what PostGIS is going to do is it's going to replace that Rast variable at each pixel with the current value. And so I'm taking that value, subtracting out, and running a small equation. And then the output of this is what the new value at that pixel is going to be. And that results in a image is shown here. So I've got all the areas where timberline are highlighted in green, and then the gradient going off of that. If you have a function that's a little bit more complex than just a single, as the one that was just shown now, you can use the PostGIS procedural language to as your callback function as well. So this is an example of that. There's three things that three inputs, and the output is again the value, the new value at that location. So our three inputs are the current pixel value, the pixel location, and then a few of your, if you have custom attributes, you can have that passed in as well. Something to notice here is that pixel value is a three-dimensional array, which seems kind of strange because you're just requesting the one pixel. But this function is pretty, STMap algebra doesn't limit you to just working with one raster. You can work with several different rasters at the same time and combine the results of each of those rasters into one. And so that's what that first dimension is doing, is it's indexing into whichever of the rasters that you're using. The next two are useful for when you're doing things like convolution, where you have a, instead of just working with one input value, you're working with several different input values and all the input values within a certain region of that current pixel. So you might have a 2 or 3 pixel boundary around each pixel that you're working with to compute the output pixel. So that's what those other two dimensions are doing there. For this example, we only have one raster. We're not doing a convolution, so we're not working with those extra values. So we're grabbing the first value of each one and calling that function again that we had in the first example. And to finalize this, we call STMap algebra on our with our callback filled out on the raster that we want. And we get the same result as before. All right, now that we've done all that, suppose that you want to output your data instead of as a raster, but as a vector. Depending on what you're doing, it might be helpful to do that. So what you can do is you can then call this stdump as polygons function, which is going to take your raster and output a polygon that represents all the adjacent pixels that have the same value. So all the values that are green are being, all the adjacent ones are being converted into a single polygon, as you can see outlined in blue there. And so the way that you would control the tolerance on this would be to use that st reclass function as we saw before. All right, so just to recap what we've done. We've done importing, and well, we've worked with rasters, brought in the geotiffs, and exported them as PNGs. We've done a few vector searches with the nearest neighbors and finding the intersecting areas of the county and the congressional districts data sets. And we also looked at how to get your data to be consistent using the st_transform function to convert between your spatial reference identification. Once we had our data into the database and working, we exported our data. It got it tile aligned using those ST overview to help us. And then we did some raster analytics with map algebra and Raster To Vectors. Here's a reference to a few of the, the data sets that I used during the creation of this presentation. They're all shown there. And that concludes this presentation. Are there any questions?
So do you have like a web app that uses this, or how you say you display it to clients? Is
we're displaying it as a web map using JavaScript and a Slippy map, I believe is the term.
Is there a client? There's several. I guess. What client are you using to pass the SQL to the database in JavaScript? Is there an API?
So we're actually using protocol buffers to communicate with the C server that interfaces with the SQL, and then we return our results back through the same pipeline to our JavaScript. So we're not connecting directly from JavaScript to the database. All right. Thank you for your time.